All right, so this is the notes for actually probably the shortest lesson in this chapter, and the only lesson in this chapter where we focus on the tangent function in terms of its graph and how it behaves. I don't even assign many homework questions from this, so we don't need to know a lot about the tangent function, but we do need to know the basics of how it behaves, and also how it does relate to sine and cosine. So first of all, what I have here is a circle, and this point, come back here. This point xy is right there. So this is x comma y. All right, so as usual, we can pretend this is a unit circle, or it can just be any circle. So if it's just any circle, then this here is the radius of the circle. It may be 1 if it's a unit circle. I'll just put r. And theta, we'll just call this angle right here. So in general, we've learned already that sine can be thought of as y divided by r, and cosine is x over r. And tangent, we've seen is y over x. I just want to kind of get a little visual of why that is. But I'll finish highlighting these things because that's so important. And again, tangent, we can think of as being y over x. Because if I look at this triangle here, we quite often make a little right triangle right here, where the y coordinate is the height of the triangle, x is the base. And so from theta, from that angle theta right here, tangent is y over x, opposite over adjacent. However, another thing we can look at is, notice I've created this other triangle that runs the height, if we just imagine the terminal arm extending, and this is the height of this sort of larger triangle that depends on the whatever theta is. And so if theta is steeper, for example, if theta is going more like this, well, that was a pretty lousy drawing. Let's try that again. If theta is going more like this, well, that's still a pretty lousy drawing. Let's try one more time. If theta is going steeper and more like this, there we go. This line in red, this height of this triangle is getting longer and longer and longer. And if theta is a less steep angle, let's say it's something like this, that line in red is shorter. Well, why am I showing this? It's not a huge thing, but if we look at this triangle here, which is a right triangle, the height of that triangle is always the same as the tangent of theta times the radius. The height of this right here is always the same as radius times the tangent of theta. And why is that? Well, if we look at this big triangle, from that angle there, I could call this x for a moment, and this is down here is the radius. So if I look at this big triangle, from theta, I have some unknown side divided by the radius. So I can say the tangent of theta equals the unknown side divided by the radius. If I multiply both sides by r, that means I get x equals r times the tangent of theta. That unknown side, again, x, the height of this triangle, is always going to be the same as the radius times the tangent of theta, which I had mentioned already. And so if the radius is 1, if we have a unit circle, then that unknown side is just the tangent of theta. Sorry, I'm working from home and things are a little different. And so if we have a unit circle, the radius is 1, and so that height is the tangent of theta. And so the tangent of whatever, the tangent of theta will always tell you the height of that line, which should relate back to one of our group problems. But I'll go back to this. However, though, really, there's nothing really inherently new here. Tangent is y over x. We've learned about that before. One thing that may be new is this little note I want to comment on right here. And so first, let me just review that sine of theta is y over r, and the cos of theta is x over r. Well, I can combine these together into the tangent function. What do I mean by that? Well, for sine, let me solve for y. And so I can say for the sine theta, if I multiply both sides by r, I can say y equals r times the sine of theta, right? If I just solve for that y there. And for the cos of theta, if I multiply both sides by r, if I solve for x, I can say x equals r times the cosine of theta. Well, how does that allow me to connect this back to tangent? Because don't forget, tangent of any angle is y over x. And that y I can rewrite as r times the sine of theta. And x I can rewrite as r times the cos of theta. And these two r's can therefore be canceled out, which leads me to this identity we called, in which the tan of theta is always the same as the sine of theta divided by the cosine of theta. And this is what we call an identity. And I've proven that this must always be true because I took definitions that we knew were always true, the definitions of sine, cosine, and tangent, combined them together to create this expression here. And so because everything up here is always true, right? Cosine is always the same as x over r. Sine is always the same as y over r. Tangent's always the same as y over x. Because I've combined these things that are always true together, this must also always be true. And this is what we call an identity, like I said. And this is really what chapter 6 is about. Not this particular identity, but identities in general. And so I just want to introduce this one right now because it's one of the more common identities. It's also one of the more pleasant ones. It's fairly simple. The tan of any angle is the same as sine over cos. But this is called an identity. And again, chapter 6 is focused on these identities. There's an infinite number of identities. In essence, we can just see from this that tangent, sine, and cos are all related to one another in this one equation. And there's countless different identities that connect all these together. That said, going forwards, it is useful to remember that tangent, anytime you see the tangent function, you can think of it as just cosine divided by cos of whatever that angle is. That said, though, that's not really the focus of this lesson. So the focus of this lesson is understanding the behavior of the tangent function. And since we haven't graphed this yet, let's start with the table. And what I have here first are some of my special angles. So 0, 30 degrees, 45, 60, 90. And then after that, I don't quite go through every other multiple of 30. But first, let's look at these ones. The tangent of 0, we've seen is 0. The tangent of pi over 6 is 1 over root 3, which I want to decimalize because I want to graph this. That's approximately 0.6. The tangent of pi over 4 is 1 whole exactly. The tangent of pi over 3 is root 3, which is approximately 1.7. And the tangent of pi over 2 is undefined. So let's just graph those for a moment. So 0, 0, pi over 6, 1 over root 3 is or 0.6, so about right here. Pi over 4 is halfway between pi over 6 and pi over 3. It's halfway between 30 and 60 degrees. And so that's exactly right here. Pi over 3 is about 1.7, so about right here. And then pi over 2 is undefined. Okay, I can't graph undefined, but let's think what happens when I just pass it. As I get really close to 90 degrees, tangent gets larger and larger and larger. As I get just past 90 degrees, tangent gets really, really negative. And again, if you're not sure what I mean, just let me go to a calculator here. There we go. And so I'll put my calculator in degree mode for a moment. So if I go the tangent of, 89 degrees, 57, right? So it equals 57. The tan of 89 is 57. If I go the tangent of 89.9, oh, the tangent didn't show up. Try that again. Tangent of 89.9. Now it's 572. Make another 9. 5,000, another 9. More, and then the closer I get to 90 degrees, the larger my output gets. And if I make this negative, it's the same ideas, but now it's all negative. So what we can see here is while tangent can't equal 90, the closer I get to it from the left, the larger my outputs get. The closer I get to it from the right, the more negative my outputs get. And so I'm describing the behavior around a vertical asymptote. And so I know, if I go back, oh, not there, getting ahead of myself. I know at 90 degrees, there must be a vertical asymptote. And so I'm going to show my asymptote right now. And not only that, I can start to kind of connect my dots here a bit. I know my graph goes to these points. And I know it just keeps going up and up forever, but never actually reaches pi over 2. And I also know that it's now doing something like this down here. And so if I look at the next values, because I have only done part of the table, if I go back here, 2 pi over 3, that is 120 degrees. Tangent in this quadrant is negative, so it's negative root 3, or approximately negative 1.7. 3 pi over 4 is 135 degrees. It's in the second quadrant, so it's exactly negative 1. 5 pi over 6 is negative 1 over root 3. Again, same values we had in the first quadrant, but they're all negative, so about negative 0.6. and the tangent of pi is 0. So let me plot those points. So I'm at about negative 1.7. Well, that's about right here. Negative 1, negative 0.6, 0. And at this point, once I go past pi, once I get into these here, I'm getting into the third and the fourth quadrants, or actually these are between those quadrants. 3 pi over 2 is undefined. 2 pi, the tangent of 2 pi is 0, so that means I know there's another asymptote at 3 pi over 2. So there's another asymptote right here. And I know it's 0 right here. So I can start to see how I can just fill in the rest now, because I know tangent starts to just repeat. So everything I drew right here, I can now just copy right here. Again, this is the first quadrant. This is the third quadrant. Tangent is the same in those quadrants. Or I should say tangent is both positive in those quadrants. And so I can start to essentially just copy what I did over here. And so this, and about right here. And then again, down here, this is the fourth quadrant where tangent is negative. And we can see now how tangent is periodic, which means it repeats, but it's not a wave. And tangent has vertical asymptotes at any multiple of 90 or 270 if we're thinking in degrees. But that's what the tangent function looks like. And so before I talk about the domain and range, let me go back to what I showed here. This is in Desmos. This is just a graph of tangent in Desmos. Notice if I zoom out, it clearly repeats on and on forever. It clearly goes up forever, clearly goes down. And we can also see here, that's a pretty nice scale, that halfway between 0 and pi, I have a vertical asymptote. Also halfway between 0 and negative pi, I have a vertical asymptote, but it repeats. Okay, so a very different sort of function from sine and cosine, but also has similarities in that it repeats, it's periodic, but yeah, it's not a wave. And so let's record some of the basic information about this. What's the domain of this function? It's not all real numbers. It's all real numbers except for the asymptotes. And where are the asymptotes? Well, you can see here, there's one at pi over 2, there's one at 3 pi over 2. There's also one at negative pi just over here. So the domain, I could just start by listing them out. So I can say x, that's a weird looking x. X cannot equal, I could say pi over 2, 3 pi over 2. The next one would be 5 pi over 2, and so on. However, what do I notice here? It's really pi over 2 plus any multiple of pi. Each one of these is exactly pi from one to the next. That's the distance between each of these asymptotes. Or I could go backwards, minus pi. So in the end, the most efficient way of saying the domain is say x cannot equal, I'll just pick one, I'll pick pi over 2 plus any multiple of pi, where n belongs to the integers. And if you look at this graph, the asymptotes are repeating every pi units. The distance from here to here is 1 pi. The range, though, is all real numbers. You made it extra clear when I showed you in Desmos. It clearly goes up and down forever, so the range is all real numbers. Again, very, very different from sine and cosine. The period, hopefully we've kind of seen now, the period is not 2 pi, the period is pi. This function repeats every pi. Literally, there's between any pair of vertical asymptotes, that is one complete period of this function. I can't use the word wavelength because it's not a wave, but I can use period. It repeats every pi. So again, tangent has a period of pi, whereas sine and cosine are 2 pi. And finally, amplitude, well, that doesn't make sense. I can't really ask you what the amplitude is because it doesn't have a max or a min. So it's not a wave. The term amplitude only applies to waves. So tangent doesn't have an amplitude. It does have a period. The period is different, though, than sine and cosine. Okay, and some key things to remember. Definitely, besides the general shape, would be where it has x-intercepts, but that's everywhere tangent equals 0, which we've learned about before, as well where the vertical asymptotes is, and that's where tangent is undefined, which we've learned about before. Everything we're doing here, we learned about in a different sense. In chapter 4, we just weren't graphing it, but we learned about where tangent was undefined, we learned where tangent was positive, where tangent is negative, where tangent equals 0. Okay, now we're showing it as a function with inputs and outputs. And so really, all I have left now is a couple of tricky problems to graph. Like I said, the key to this lesson is getting a sense for the behavior of tangent. So let's graph this and this one. Okay, so first I want to graph tangent of not x of pi over 6x. So I can see the only difference between this and tangent is that I have this b value. So this represents a horizontal stretch by a scale factor of not pi over 6, but 6 over pi. Well, that's not wrong, but that's not terribly helpful in terms of, that's kind of a weird scale factor. However, what's going to be more useful, I think, is actually find the period. So I can say, therefore, the period of this function is not going to be pi, it's going to be pi divided by the scale factor. Pi divided by, sorry, pi times the scale factor, or pi divided by pi over 6, which is the same as pi times 6 over pi. Notice what I did right here is identical to what we did with sine and cosine lots. The only difference is I have pi in my numerator instead of 2 pi because the period of tangent is not 2 pi, it's pi. And so that said, these cancel out, and so my period is exactly just 6. And so more useful than stating that there's a horizontal stretch by a scale factor of pi over 6 is to figure out the period. That, I think, is much more useful. The period of this function that I want us to draw is 6, not 6 pi, 6 whole. That's the only transformation, which means the graph here should have the same behavior as what we had before. There's no translations, except the period is going to be 6 units. Every 6 units there's going to be an asymptote. But it still should start at 0, 0. If I look back up here, you know, that point right there is 0, 0. If I stretch that horizontally, that's not going to change. What's going to change is where this vertical asymptote is, and all the vertical asymptotes. And so one thing I could do is I could literally take that pi over 2 and times by the scale factor. And I'll do that, but there's another option. So I could, that vertical asymptote, which was at pi over 2, I could times by the scale factor, which again was 6 over pi. My pi's cancel out. I get 6 over 2, which reduces to 3. So I know at exactly 3, I'm going to have a vertical asymptote. However, ideally, I didn't really even have to do that, or what I'm about to say makes sense. If the period is 6, and I know tangent starts at 0, 0, then I know there must be an asymptote 3 to the right and 3 to the left of 0. Because I know the period is 6. And therefore, I know another asymptote is going to be at 9. And so, well, what I did right here, it wasn't wrong at all. In some ways, I like better just realizing, okay, if the period is 6, there must be, you know, one asymptote, half that way and half this way. In this case, 3 each. Other than that, I'm just going to draw the sort of general shape. I just want to sketch, so I know it kind of goes up and goes like this, and then just repeat. I know halfway between these asymptotes, it must have an x-intercept again, and it's the same sort of shape. Now, one common mistake is people show around the x-intercept, they show it kind of going flat like a multiplicity of 3. Okay, that is wrong. I mean, if I just go to Desmos, for example, it doesn't look like that. It doesn't flatten out. It doesn't look like a cubic function with a multiplicity of 3 at that point. In fact, if I zoom in enough, you know, that looks like a 45-degree line. In fact, it is. At the instant it's crossing, it is a slope of 1. It's a y-intercept, sorry, 45 degrees if you want to think about it that way. So it's definitely not flattening out. And so while, again, this is not an art class, you know, those are distinctly different. And so we do want to know, again, the general behavior of it. So again, something like this. There's my graph of the tangent of pi over 6 times x. Okay, and the last one, which seems extra weird, is I want to graph this. How can I approach this? Well, the key to this is first algebraically seeing if there's a way I can rewrite it or simplify it. And the key to this is remembering what I mentioned at the beginning of this lesson, that tangent is always the same as sine over cos. So the tan of x, I can always, if I want, write it as the sine of x divided by the cosine of x. So all of that times 4 times the cosine of x. Well, then I can see I can cancel out a factor of cosine here and here. So this behaves just like 4 times the sine of x. Well, I know what the 4 times the sine of x looks like. That is a sine wave with an amplitude of 4. So let's sketch that, but then there's one last thing I have to be careful about. So I want to sketch out a sine wave with an amplitude of 4. So sine starts at 0, 0. It has another x-intercept at pi, at 2 pi, negative 2 pi. These are all the x-intercepts of sine. And so this, you know, 4 sine will be the same if we're just vertically stretching it. The only difference is halfway between these points here, the highest point will be at 4 instead of 1. And halfway between these 2 points here, the lowest point will be at -4 instead of -1. And now I've sketched out one full cycle of it. Okay, but that's it. It's pretty easy for me to draw another cycle, so I'll do that right here. But like I said, there's actually one last little detail that I really should think we can think about now. There we go. So this is my graph of 4 times the sine of x. But if I look back up here, let's think back to rational functions, because there's actually a restriction right here. And it's hard to tell, but cosine of x cannot equal 0. Not x, the cosine of x cannot equal 0. And that's because if the cosine of x equals 0, right here, I'm going to be dividing by 0. And we can't divide by 0. And so let's think, where does cosine of x equal 0? Well, cosine of a function equals 0 at pi over 2. And then at 3 pi over 2. And then at 5 pi over 2, and so on. Which means my graph should look just like the graph of the sine of x with these restrictions. But I know they can't be asymptotes because I know it looks like the graph of 4 sine of x. So hopefully with what we learned in a previous unit, we can realize these actually must be points of discontinuity. It's the only way that it can look like the graph of sine x, yet have these parts that x cannot be substituted with. It's the exact same idea that we saw from chapter 9 when dealing with points of discontinuity. And so I want to show a point of discontinuity everywhere the cos of x equals 0, or at pi over 2, 3 pi over 2, negative pi over 2, and so on, everywhere cosine equals 0. And so the graph I have here is great, but like I said, I want to make it a tiny bit better. So at pi over 2, which is right here, at 3 pi over 2, at negative pi over 2, at negative 3 pi over 2, all these places, cosine equals 0. So at all these places, this step right here, I'm going to be dividing by 0, but just at those points. So I'm going to go to my graph here, and I'm going to make a little hole right there, a little hole right there, and here, and here. Now, if we hadn't learned about points of discontinuity already, I couldn't ask you a question like this because, well, we hadn't learned about them before. But again, these are all points of discontinuity. And there's an infinite number of them. And this also leads into chapter 6. In chapter 6, we start looking at the restrictions of these expressions as we simplify them. And again, right here, when I simplified it down to 4 sine x, that was correct. But however, there were restrictions, and I really should say where x cannot equal, well, these values over here. So again, these more challenging questions are connecting some things together. In this case, I'm leading us into some parts of chapter 6 because we are getting very, very close to that. However, like I keep saying, there's not a lot to this lesson I need you to know. The key aspect is, how does tangent behave? Some basic transformations on it, very, very basic. As well as it is now useful going forwards to remember that tangent is always the same as sine over cos. All right, that's it. That's it.